task sequencing problems arise in various robotic applications in radically different ways. Sequencing is coupled with different types of decisions on how the tasks are executed. In many applications, such as robotic pick and place, the inverse kinematical solutions belonging to given task space poses must be chosen. In laser cutting, the directions of the cuts and the contour entry and exit points are strongly related to the cut sequence. Finally, in remote laser welding and robotic quality control, the viewpoints must be chosen. Moreover, the sequencing problems can be defined in different dimensions, such as the 2D or 3D task space or the 6D joint configuration space of the robot, and relevant optimization criteria and site constraints can vary. Accordingly, scientific literature and industrial practice are both dominated by dedicated solution approaches for individual applications. Yet, the overwhelming majority of these approaches rely on common mathematical methodology, and the arising sequencing problems can be formulated as some extension of the well-known traveling salesman problem. Our objective with the development of ProSeqqo was to offer a generic problem description language to capture typical task sequencing problems arising in industrial robotics. Based on the description, ProSeqqo computes close to optimal plans with computation times suitable for online planning. Our approach is based on a problem description language easily editable by domain experts, even without a deep background in combinatorial optimization. The problem descriptions are transformed into a generalized traveling salesman model and solved using a combination of local search techniques from Google OR tools and some custom algorithms. The robotic task sequencing problem can be formulated using a hierarchical representation. We illustrate this on a camera-based robotic pick-and-place application where the robot must localize the parts arriving in bulk, pick them one by one, and place them precisely to a part folder for further processing. Processes are the largest units of work that must be sequenced. In the pick-and-place application, one process belongs to each part. Alternatives correspond to different ways of executing a process. In pick-and-place, each alternative corresponds to a possible grasp for the given part. Each alternative consists of a series of tasks, here a picking and a placing task for the part. Each task can be executed using one of the candidate motions, where each motion visits a sequence of configurations. In pick and place, different motions correspond to different inverse kinematical solutions for a grasp on the part. Precedence constraint can be defined on two levels, between two processes or between two motions. Since a motion may or may not be executed in the resulting plan, the latter is a conditional precedence constraint that expresses a logical relation between the execution mode and the sequence. Finally, problems can be cyclic or acyclic according to whether or not the robot must return to its starting configuration. ProSeqqo searches for a plan that minimizes the total travel cost along the robot path. The cost can be calculated using one of the various built-in cost functions, such as the Euclidean or the Manhattan distance, or the travel time assuming limited joint velocities and accelerations. Resource changeover costs or penalties for idling between effective tasks can also be captured. If needed, custom travel costs can be defined in matrix format. The problem can be encoded in the custom text format called Seqqo, as shown in the video, in JSON, in XML, or submitted to the solver via an API, which enables using ProSeqqo in complex planning workflows or in online planning scenarios. In experiments on the camera-based pick-and-place application with up to 30 parts, ProSeqqo could find close to optimal solutions in 0.1 to 1 second, which enabled the application in online planning scenarios. In particular, the guided local search of Google OR tools provided a consistently good performance. Yet it was crucial to use the appropriate GTSP representation from the various formally equivalent representations. ProSeqqo was implemented as a platform-independent Visual Studio C# solution. It runs as a command-line application or a DLL accessible via an API. It also includes a visualizer built on top of the Helix toolkit. ProSeqqo is available open source on GitHub, together with various examples and its documentation. The link can be found in the caption below the video.